Good morning. Our next speaker is the Dr. Eduardo Manrique. He is chemist, BAs and PhD from the Universidad Central de Venezuela, with the more than 32 years of the experience in the oil and gas industry, AUR, EUR, and oil field chemistry in more than 13 countries. He is now working as technical authority reservoir and EUR in ACP Ecopetrol, Colombia. Dr. Manrique has participated in more than 8 publications. Today, present importance of oil burning alteration in low salinity water. Welcome, Dr. Eduardo Manrique. Thank you for being here today.
Good morning, good afternoon, or good evening, depending on which part of the world you are located. Here is speaking Eduardo Manrique. Sadly, my camera in the laptop is not working properly, though we are gonna see each other tomorrow. Also, thanks for the opportunity to present at the IEA. I have been involved in this group for so many years, and I have learned a lot in different topics of enhanced oil recovery. And today I'm going to summarize the R&D activities we're performing in Ecopetrol in the area of low salinity and SmartWater flooding. And specifically, we're going to talk today about the importance of oil and brine interactions in low salinity water flooding. I also thanks to my co-authors, and this study is part of the PhD in petroleum engineer of Gustavo Maya and the postdoc in chemistry of Dr. Carreño. They gave me the opportunity to summarize what we have accomplished so far. The outline, we're going to briefly go to a background and motivation, introduction and scope, very briefly the protocols we are considering to understand the interactions independently and together in the oil brine rock system, some of the results, and a summary conclusions. Regarding the background and motivation, it's well known in the industry that crude oil contains salt and heavy metals. So another thing that we also know that reservoir fluids are in contact for a geological period of time in reservoirs. Then, we produce this oil, we treat this oil, and we perform multiple analyses. And one of those is the assays we run in the crude oils. And I'm highlighting few of them, and in red, just the information we're going to be discussing today. Salt content and the evaluation of calcium, especially calcium and magnesium in the system we are evaluating today. And why is this important? Because, well, in companies like ours, where we have the whole production chain until refinery, the first step when we transport the oil, the crude oils are going to the salting units. And this is just to remove all these salts and other contaminants to minimize corrosion and other issues like potentially contaminating the catalyst, inhibit the catalyst. These activities performed at these temperatures, and they use fresh water. So I'm using this desalting unit as an analog of a low salinity and how much information you can get out of there. I recommend, if you have access to this information, you can understand what I'm talking about, the amount of salt and other chemicals released by the oil before it's going to distillation and its refining process. Regarding the benefits of low salinity water flooding are well documented in carbonate and sandstone. I'm not going to go over it. Multiple mechanisms have been proposed. Given that is almost reservoir specific, we cannot reach a consensus what will operate in this or other reservoir. And the studies we're doing, we started with a challenging reservoir in 2018, which is we have run several pilots here, water flooding, ASP, gel treatments, but this reservoir is a sandstone in a depositional environment, which is marine transitional, which means that it's a sandstone, but the cement is carbonates. So we have a lot of dolomites, calcium carbonate in the cement. So in order to understand the oil interaction with the waters, we took the oil and worked with different low salinity brines, including synthetic formation brine, and validated that we form spontaneous dispersion. We increase a lot the water soluble organic compounds, and the ionic composition also increases in water test at reservoir temperature for different period of times. This was presented in the last conference, IEA conference in 2019 in Cartagena here in Colombia. Once we understood this, then we start, okay, let's see, first of all, well, how my low salinity brines interact with Berea rock. We decided to move to Berea rock to understand the interactions of the fluids in a system, in a rock system that is less reactive than the one we are evaluating. And after we did that, the most important advantage we are using here is that we were able to use capillary electrophoresis to analyze the effluents every 0.25 pore volumes injected. Here we need just 20 to 30 microliters to analyze cations and another 20 microliters to analyze anions, including low molecular weights organic acids. Once we understood the kind of the baseline, we then also run corefloods, sequential corefloods, and we didn't use, in this case, in this study, we already are comparing sequential corefloods versus independent corefloods. With that, I just summarized coreflood. You know very well this system. Here is the basic oil composition data. Acid number is low, but despite this apparent low salinity, it is very reactive, and the conditions of the coreflood or displacement efficiencies we use. We use a synthetic field brine, and some cases we dilute it with deionized water, and also potassium chloride, magnesium, and calcium chloride salts to validate the interactions we are summarizing today. The first sequential low salinity water floods, well, we reported these studies in 2020. Field brine total salinity is around 8,000 ppm. We saturated with oil, then run water flood with the same field brine, and then diluted with deionized water. A similar experiment, we decided, well, we saw these results, well, let's include an additional step, and we resaturate with oil and test the lower salinity field brines to compare the results and see if there is any difference. Next step was to run Berea corefloods without oil and alternate field brine, low salinity specific brine of magnesium chloride, field brine, KCl, field brine, and CaCl, and without oil, and then repeat the same system with oil, resaturating in each step with original fluids. Just to get into the results, the first experiment, just in tertiary mode, water flooding with the field brine. We diluted 50%, so a small increment and no further increments were observed. The most interesting thing here is that, okay, this increment in displacement efficiency can be correlated to this increase in differential pressures in the system. And we already validated that this oil with waters, low salinity waters, can form a dispersion. So it's very reactive, this oil. Okay, in this case, the next step was, okay, let's compare that with the similar experiment. And we noticed that in every single endpoint, we change the condition of the core. So initially we started with field brine, then diluted 50%, and then diluted 93%, and the recoveries are here. However, we noticed that the endpoint's initial oil saturation was totally different in each of these steps. Knowing that Berea is not a reactive rock, we start looking in more detail. Well, how can we explain the behavior of this oil in Berea sandstone? In this particular case, we move to the interaction first, only brine and Berea rock as a baseline, following the protocol you are seeing here. Here you see the ionic composition of the field brine, magnesium chloride, potassium, and calcium chloride. And what we did in the effluents was, okay, let's inject field brine, and I was analyzing chloride, and the dashed line is the injected concentration, and the produced is the light blue line. So in this case, we follow the field brine. In this step, we start injecting a lower salinity magnesium chloride. We see the decrease in salinity. That's what we call the low salinity effect. And then we reach the chloride concentration of the injected magnesium chloride. Then we switch again to field brine, then KCl. We reach again the injected concentration, repeated, and the calcium chloride was slightly higher, but more or less was a condition that tell us that, okay, this porous media is not really retaining or changing much. We also compare that with every single cation. For the sake of the time, I'm just comparing here the injected and produced magnesium and calcium. In this first experiment, the same sequence, field brine, the calcium content and magnesium content are shown here. 40 ppm of magnesium, 503 ppm of calcium. Remember that this reservoir is coming from a carbonate cement. This is where calcium and magnesium is coming. Then when we switch to magnesium, the decrease in calcium is evident from this dilution of the 503, and the magnesium start to increase because it's what I'm injecting, but calcium reached 0, so there's no major indications. I'm not plotting here that differential pressures are not relevant to consider that there is a important brine rock interactions in this system. Then we reinject field brine, the same, then KCl, both calcium and magnesium reach 0 because we are not injecting neither of both cations, and repeat it for calcium chloride, and the same, magnesium reach 0. And from this, the conclusion was, okay, we can use this rock to infer what's going on with the oil and this brine system we are injecting here. So here I'm showing the experiment, the first displacement efficiency, which is the injection water flooding with the field brine. This is the composition, and I'm highlighting in yellow the elements injected. The dashed line is the injection and the solid lines are the produced. And if we can see here, we can say that there is some level of equilibrium. Both fluids or similar fluids have been in contact for a geologic period of time. There's not much ionic exchange between field brine and oil. The only thing to highlight here is that at the end, very end of the 6 pore volumes, we start producing some potassium, which is not, it was not detected in the original field brine preparation. From this, if you notice, this is a very flat dilution. The ionic composition is very similar to the injected one, but then we're gonna jump with magnesium chloride. We didn't see much effects. Then we move to potassium chloride. In this case, it's very interesting how the ionic exchange between it was observed in this experiment. First, we notice the low salinity. Well, this is 8,000. Remember, the chloride, the total salinity, it is just go to very low salinity because we're injecting 1,000 ppm of KCl. And in sodium, you notice that it's going down. Calcium is also going down, getting diluted. But then in this experiment, we notice the production only for short period of time of organic acid anions, which are formate and acetate. What's interesting in this equipment, capillary electrophoresis, we can measure all these elements at the same time. And the most intriguing thing here, look at the green curve, which is calcium, and the yellow is magnesium. Why, if I'm not injecting magnesium and calcium, I'm producing both cations in the system? We already saw that Berea core doesn't have calcium or magnesium in their composition to justify the increments observed here. So this is what we believe is the ionic exchange and the dissolving of the crude oil in the porous medium, as I presented in the introduction. And look at the purple line is the potassium produced, which is the cation I'm injecting until it reaches its level of close to the injection concentration. The chloride, after decreasing the salinity, stayed very stable, close to the injected concentration, around 560 ppm. So this example is very interesting in how the chemical composition, because the oil and the brine of lower salinity can impact not only SmartWater low salinity, but several recovery processes, specifically chemical EOR. Now we switch from potassium chloride to calcium chloride, and in this case, we notice again a very stable system. First, the ionic exchange is not that active like the previous experiment, but then of course we saw the low salinity because we're injecting in this case a higher saturation of calcium chloride, 2000 ppm. And if you notice, there is a decrease in salinity, decrease in calcium, because we're injecting lower salinity, but at some point it reached the injected concentration. And we can notice that there is not much ionic exchange. What I'm saying is that probably calcium and magnesium, let's go first to calcium and magnesium, are kind of stable and in pseudo equilibrium with the oil. So there's no exchange because there's no need for transfer. Let's say the oil is already saturated with calcium and magnesium, and there's no need for exchange. In this particular example, we notice a little bit longer the production of formate and acetate. So with this, what we try to say is, look, there is an important mechanisms here that probably we are not looking with this level of detail, and in some cases, who knows if the cationic exchange reported in some publications are related to these effects and not related to rock and brine interactions. Chlorine is again very close to the injected concentrations. From the displacement efficiencies, we noticed that only with potassium chloride and calcium chloride, we observe increases in differential pressures that we attribute to the microdispersions observed in bottle tests. We are trying to see if we can define some methodologies beyond microfluidics or CT scan to understand a little bit better this mechanism. But at least from these examples, it is clear that understanding the oil brine system, we can tweak the water injection to get the most benefit of SmartWater or low salinity water fluid. Again, in these experiments, we also noticed the change, the changing the endpoints. Water saturation look as the same coreflood is resaturated every time. The initial water saturation is lower and increasing the initial oil saturation and the displacement efficiencies. We see that the field brine is even better than magnesium chloride from that standpoint, and we don't see any differential pressure effects. Then we start moving again back a little bit with KCl, and the main benefit was observed with calcium chloride. So with that, I just summarize the importance of this interaction. The sequential injection is very useful to understand ionic exchange and reactions, possible reactions with and without oil. And the benefits of capillary electrophoresis was a huge advantage for these experiments. However, to interpret displacement efficiency, probably the sequential injection mode is not a good idea, but we are at this point, we are comparing these sequential corefloods with independent corefloods that to validate that what we are seeing is not an accumulated effect from all the brines injected in previous stages. Finally, we demonstrate the importance of these interactions, salting in or salting out effects in low salinity waters that can help us to design better SmartWater. And in our consideration, these effects have been overlooked, and we require further investigation to improve our pilot design. These results will be submitted to Fuel Journal and hopefully will be available soon in the literature. Again, thanks for the invitation and looking forward to discuss with the team tomorrow. Thank you.